To all. On behalf of Department of Electronics Engineering, I welcome our today's speaker, Mr. Deepan Raj sir, Senior Technical Lead from HCL Technologies. Hearty welcome to you, sir. Now I invite our coordinator, Dr. V. Satish Kumar sir, to give an introduction about Mr. Deepan Raj sir. Over to Satish sir.
Thank you, ma'am. So it gives me immense pleasure in welcoming Mr. Deepan Raj, Senior Technical Lead Data Science from HCL Technologies. He has 8+ years of work experience, and his research interest includes artificial intelligence and robotics. He has conducted or delivered lectures in more than 750+ workshops or events. So he delivered lectures at IIT Madras, IIT Delhi, IIT Bombay, Indian Institute of Science, Bangalore, IIT Tirupati, NIT Calicut, Madras Institute of Technology, VIT Vellore, Chennai, Amravati, SRM, etc. So he has been a part of the Indian Book of Records for conducting AI workshop to 700+ students in a single day. He has also conducted corporate training at Nokia Solutions, Ponder New Technologies, Smart and IT Solutions, Notus Soft IT Solutions, Orient Technologies, etc. So it's a great privilege to have you, Mr. Deepan Raj. So now the session is yours.
Yeah, thank you, sir. Yeah. Yeah. Good evening, everyone. Let me share my screen. Yeah. So today's topic. I hope the screen and my voice is visible and clear. Yeah. So let me start with the topic right away. Yeah, today we'll be focusing towards the evolution of GPT models. Like, how did we get to this point of having this GPT models and a lot of generative AI based models at this point? So we'll try to understand the journey of NLP, like how we have started with different architectures to solve problems, and how that particular architecture evolved to solve the same particular problem in the most efficient and the better way. So that's the ideology behind this particular session. So let's go a little deeper into it. Yeah, we all know that computer vision has a very huge success over the past period of I would say before the introduction of transformers and GPT models. So till that, computer vision is some to be one of the best or the successful models in AI, because we had many successful architectures in computer vision that gave state of the art results, and also it has been deployed in many different real time products and problems. So but not only that, even NLP has such kind of improvements in the later stages. But let's try to understand like how this improvement happened. So in order to understand natural language processing, or in order to train such models with an NLP as a data, we need to have only one important aspect into it, that is understanding the data itself. Okay, so if we take images has pixels inside, correct? So every pixel is a number basically. So if you have it as a number, the model can understand the components and nuances inside it at some point of time. Once the architectural complexity increases, the model gained ability to understand images in a far better way, because the representations are much natural in nature. The naturality in the sense, like, because everything are pixels and pixels are numbers, we don't have to do anything on that. We just have to feed the data to the architecture, and architecture does wonders to us. But when it comes to NLP, things are little difficult, because NLP are just words, right? So the words have to be converted into numbers first, which means that we have to find an effective way of vectorizing or tokenizing the data, such that those data can be converted into numbers, and that numerical representation of those words can be pushed into your model training, right? So let's see like how in the early days we have started doing this embeddings, or vectorization of words. So people or researchers believe that, okay, it's better to go with character based encodings, by assigning numbers for every characters, such that like the representative can be very limited in nature, or you can easily spin up numbers by just arranging all the characters together, with all the numbers together. So that proven to be the starting way of vectorizing these words. But the biggest problem, or the biggest challenges, was to differentiate between similar words, that as not only like placement of the words, placement of the characters, but at least the numbers are present throughout the word. For example, if you see silent and listened has the same characters, but the positions are scrambled, right? So which means that when it enters into the neural network, right, so all these are termed to be numbers. When we add or do some mathematical operations, the results which you get for silent and listen would be very similar against each other. So that created a lot of problems, or a lot of dilemma within the neural network, making its understanding of these words little difficult. So which means that yes, this character based encodings are not doing a good job. So that's where people started to use word based encodings, right? So where we had vectorizations of every word, creating unique numbers for every word which you see in the sentence. So in this case, you see, like, I've given four numbers, like I love my dog. So where I've given 1, 2, 3, and 4. In this case, let's say if I get a new word, let's say I love my cat. Okay, I guess it's not that visible. It's basically high. There is some sentence hidden here. Yeah, I hope you see that. Um, Imagine, like, I have another sentence like similar to I love my dog, but I have a new word named cat. In that scenario, I'll add a new number towards that particular word. So which means that whenever a sentence contains a unique word, for that word, I'll be adding one more number towards it. So this way, word embeddings can be, created for every unique word occurrences. So now the problem in this aspect is, imagine, I have a word king, and I also have another word emperor. So basically, these two words are the same, right? So it conveys the same meaning. But what if the word king is given number one, and the word emperor is given number 20? So basically, when these two words are interacting in the neural network, the network, finds it little difficult to digest, because of the fact these two are somehow conveying same meaning, but the number is too far away, making the model to force itself to, to understand these two words are different, not giving the same meaning. So that created a dilemmatic problem inside neural network again. So yes, still, word based embeddings is a real big problem. An efficient way to create these numbers are yet to be discovered. But yeah, having said that, yes, word based embeddings was little successful when you have a limited data set within yours. You can easily turn tides. So that's that was still 2013, I would say. And that's where people realize, okay, so I need to create something, some sort of vectorization method that can convert every word into a vector, but those vectors, or the words that have similar meanings, should have those vectors aligned very close to each other. Okay, imagine you have the word king and man. For king, I might have a 16-bit vector or something like that, where imagine, like, I have like values like 1, 2, 4, and 5, and for man it should be like 1, 2, 4, and 6. So the variations of these two numbers will be very minimal, but yes, ultimately, like, every word will have a unique number representation, but the magnitude of the change will be very, very less. So this proven to be more effective, than randomly assigning numbers for every word in the given sentence. So people decided to create a network, or a method. I'll come to this point, in the later stage of this presentation. But this word to vector created a very huge, you know, you know, a drift in the field of NLP, where creating or vectorizing the words that has closer meanings will have closer magnitude. So that maintained the stability inside vectorization of the words, and also making sure the network learns the contents much more faster without any dilemmas. So that's where few problems about NLP got was solved, actually. because as you know that I would say still, even now, even after GPT and many models has been deployed, still this vectorization of words can be improved even more better. So that's one open or debatable question, I would say. But yeah, there are a lot of concepts are yet to come. But let's try to understand the second problem in the hand, that is your sequential network. Imagine I create a sentence like this college is very good. I stop it there. The question is, uh, the particular sentence which I've told right now, whether it is positive or negative. It's a positive sentence, or since I've used the word good in the sentence, like this college is very good. Basically, the word very good ended on a positive note, which means that this particular sentence is a positive sentence. But what if I use or end the sentence with the word but? This college is very good, but I stop it there. Now what happens, because of this new word, the probability of this positiveness of the particular sentence would have been reduced, right? Which means that in order to understand the sentence, the entire sequence have to be kept in a fashion so that you understand the sentence very properly. So to understand natural language processing, it is required to have a sequential mechanism that can hold previous inputs, or that can make sure the network interacts with the previous data and the current data together to create a better insightful result. So that's where people started creating different architectures rather utilizing your normal feed forward network, your normal day-to-day networks which you see, right? So instead of using that kind of architectures, people decided, okay, let me go with a different mechanism that is little sequential in nature, or that can handle sequential data in the first place. And also it can keep the previous informations or previous inputs into consideration, or a sort of memorization of the previous data together. So with these kind of combinations, people created a network known as recurrent neural network, which was very popular, especially in terms of handling a sequential data. This is a popular choice even now. Let's try to understand RNN, a little bit detail into it, so that we'll get to understand like how this started, NLP journey to the next stage. So this is the formula behind recurrent neural network. We see here, we have imagine, give me a second. Yeah. So imagine like, if I remove this particular section, okay, let's say like I don't have the section. If at all, if I remove this t suffix or prefix, uh, the time factor out of the formula, this would become a simple feed forward network. Agreed? Because you have the event state, that's your gradient output. This f of w represents the weight and the activation function. So weight and activation functions is inside this f of w, and x of t or x is going to be your input, right? So a simple feed-forward network will look something like this. Now, if I add the previous gradient or previous output of the network into consideration before I, calculate the next new state h of t, that is what current neural network is all about. Okay, you take the previous data and push it to the current calculation into consideration. Okay, so the formula would change something like f of w of h of t minus 1 comma x of t. So the x of t represents the current data, and this is the old state data. Okay, and this would be the weight value and then activation function. So just elaborating it a little bit, to make to give a detailed sense onto it. So basically, I'm just converting this f of w into activation functions and weight. So I will have a weight for h of t minus 1. I have a weight for x of t, and I have an activation function tan h, and finally I do get a output that's called h of t, or can be termed as y of t, if it is the last output. But nevertheless, now this h of t will be traveling to the next set of layers as a previous state input. Okay, so, or sorry, previous state output. So this inclusion of previous state output in the network calculation made the recurrent network much more powerful in handling a sequential data, because it can understand what happened in the previous stages, giving it a better ability to perceive informations, or link informations with the previous data together. Now let's see the computational graph within it. So imagine there's one important aspect in this case. Okay, so this is just one single network representation. Okay, this RNN is something like a it can be of any number of layers. The only ideology is like the output will be fed back as a loop in a recurrent fashion to accommodate or to be given as the previous state input or previous state output to the current stage input. Okay, something like that. So that's what we have unrolled it here. So this is basically one single network that has been unrolled in a matter of time step. Okay, so like these are like events which is occurring in the future, something like that. Okay, so imagine this x1 is the current input. Okay, so that enters into the network. You have h of 0, that's your previous state output. Literally, like in the initial stages, this would be 0, right? So this can be 0, and this x of 1 is going to be your input. And when these two interacts together, you get some result that will be termed as h1. Now this h1 will be entering into the next stage, that's for your input x2. So imagine these are words, or this can be bunch of words. Let's say this can be A, B, and C. Okay, these are three words. So it can be either three words or combination of words together. Okay, making sure we have adequate time step to accumulate all the data. So the word A enters, you get some result, you get some output of h of 1, and when the word B enters, the context of A is present inside this h1. This h1 contains all this information of this A value, or the input x1. Similarly, when an x3 enters, when the word C or the input x3 enters, the context of x2 and x1 together will be available in this h2. Okay, h2 will have the contextual information or some information about x1 and x2, so that the decision is up to make, which has to be made with x3, will have some weightage over the previous data together. Okay, so that's the basic idea behind. So this previous data gives, or is given weightage in a manner such that only the new data is not considered, also the old data is in the loop to be considered. Okay, so this is how an RNN or a recurrent neural network works basically. And yeah, so obviously you're gonna calculate the loss. All these things are gonna be the same. Okay, the only difference is how you're gonna calculate these losses. It can be of intermediate stages. Let's say imagine you have intermediate outputs at every stages. Let's say text generation, generating text from one language to another, or giving an input and expecting a summary written, or vice versa, like giving an entire bunch of content and summarizing the content. So everything is like many to many inputs, right? So for those kind of scenarios, basically you can get multiple stage outputs, or you can also have a single stage output. With that, you compute a loss calculation. All the basic loss calculation like cross entropy will be utilized here if it is a classification problem. Mostly like it's going to be a classification or a regression problem. So the similar loss calculation will be applied. The only difference is like it's going to average things out if you have multiple stage outputs. That's all. And during the back propagation, it basically update the weight in a more common fashion, so that every data's been considered into it. Because you see, like, this is just one single weight, it's not shared, it's just basically one network. It has been unrolled in time steps. That's all. Got it? So that's another essential thing to be kept in mind. Okay, so you have a shared weight. Imagine, like, if at all it's like a rolled out network, the weight will be shared. And basically, you know that this is a single network that has been rolled in period of time steps, inevitably having only one weight file towards it. Okay, so that's how a recurrent neural network is created, and it is proven to be successful in the early stages where where we had a lot of sequential problems in hand. But nevertheless, we did had multiple problems inside it, especially having this exploding gradients and vanishing gradients, which created a lot of problems, when handling a huge amount of data, or especially sequential data. So there's two aspects towards it. One is exploding gradients and another is vanishing gradient. So as the name implies, uh, exploding gradients are something where you have those gradients, right? So gradients are these h values. So h1, h2, h3, all these intermediary values which has been calculated. So imagine like these values increasing, since it is being unrolled, multiple times, or in the form of a time step. Basically, the value of this h1, h2, h3 will exponentially increase at some point, leading it to explode into a very big value. That is quite possible given the nature of your calculation which is happening. You saw the formula, right? So you just additively add the weight and the states, you add the current data and the weights towards it, and do an activation functions and be done with it, right? And again, the most commonly used activation functions would be sigmoid and relu. So these two doesn't have any negative compensation, so making it to be even more susceptible to this exploding gradient. So where the number will explode at some point of time, given the situation of the inputs which has been entering. So that is a potential threat because of this exploding gradient. The later stage of the inputs will not have much importance, will not be given more importance because the gradients would have been exploded at some point of time, and the outcome of the later stage or input might not have better opinion because of the huge number which is there. All I'm trying to say is like, you have the formula, right? So where you have the old state representation and the current state representation. Imagine the old state representation has a value of 10,000 and the current state representation is just 0.01. So the 0.01 doesn't have any value because you have a very huge number here, right? So that is a potential problem, and this will exponentially increase over the period of time, and it makes the model more difficult in nature to understand the nuances of the data. But yeah, so having said that, there is also another backward point towards it, that's like vanishing gradients, which we can discuss in the next slide. But basically, this exploding gradient can be somehow tackled with the concept known as tanh activation function. I guess it's not there. Okay. Yeah, so we have tanh activation functions, right? So basically, you'll have a representation of -1 to +1, right? So this is like +1 and this is like -1, this is minus infinity to plus infinity. So the input is from minus infinity to plus infinity, then the outcome will always between -1 to +1. So yes, it is a nonlinear representation or nonlinear activation function, but the outcome is somehow maintained between certain set of values between -1 to +1. So this addition of this negative information, or giving negative value in the process, reduces this explode gradient, clipping the number into a certain range so that it won't explode. So thus introducing tanh activation function within your recurrent neural networks maintained or somehow maintain the exploding gradient problems. But yes, people also use truncated back propagation. Instead of back propagating entirely back, they use a truncation mechanism. Like, you take last three time steps, you back propagate, you update the weight. Take the next three time steps, you back propagate and update the weight. Likewise, you do a truncated back propagation so that the gradient are still alive and you maintain the values or the magnitudes in a better way. Yes, again, tanh proven to be very effective and reducing the exploding gradients. That's very good. But there's still another problem. What if the gradient vanishes at some point? Imagine like you have 1,000 time steps. At some point when you back propagate, you know, the value which you have will diminish over a period of time, giving no information whatsoever. So the information will be lost at some point of time, because the gains are too are very small to be noted down. So which means that the coming informations will have more opinion than the current one. So that is also another important thread, that is basically forgetting informations because the sequence is too lengthy. you know Imagine you have a sentence that is like 10 words. It's very easy to understand or keep in mind, correct? But what if I have another sentence that has 1,000 words? So imagine, like, when the number of words increases, the longevity or the length of your time step is also going to increase, or the amount of information which you're going to hold will definitely increase for sure, right? So with those things happening in the background, this vanishing rate became a potential problem over the period of time. Okay, so that paved a way to another architecture named LSTMs. Okay, so yeah, I'll just stop for a minute, just asking, do we have any doubts or clarifications before I proceed to the next stages of the networks? All right. Okay, I hope everyone. Okay, sounds good. All right, so okay, so I guess everyone are onto the track. Yes, so let's go for the next part of it. Okay, so where we try to tackle this vanishing gradients with a concept known as LSTM. Let's try to understand that. Okay, imagine, let's take this example, where you have a sentence that is giving a feedback of a particular product. And you see, like, there are some, contrasting words like amazing, perfectly balanced breakfast, will be buying it again, and some more contents inside it. But if you see, like, the highlighted contents are very essential for me to classify whether this particular feedback or review is positive or negative, right? So, and as I see these words, I would say these are positive in nature, correct? Yeah, because of the important words like amazing and all those things which has been highlighted, uh, proved it to be positive in nature. Okay, but if at all, imagine when we perceive information in terms of a network, what happens, like, the first word will enter into the network, right? So we get some information about this amazing word, and then slowly, like, it takes word by word and word by word. At some point we'll be at this end stage, we'll be having this be buying again. Imagine the contents are too positive in nature. At some point of time, the previous state information which I'm going to get here is a summation of all these information together. The entire information is put up together, in a form of previous state like h of t minus 1, when I perceive with this information b, or buying. So at some point in time, all these important words like amazing, perfectly balanced breakfast would be like combined inside it, and we might not know, or we might not give more priorities to those later stages words, or the previous words which is there, right? So that is a fundamental problem which I was talking about, in terms of vanishing gradient, where this words or the gradients will vanish over a period of time because of a lot of monotonous numbers that, or monotonous words that enters into the sentence. So having said this created a method. What if I have a mechanism that can save, or more literally, not like a saving, but have a mechanism to hold down these information into into a much better way, or a much longer period of time. That would definitely solve most of the problems, right? So basically, the idea is, if I can hold information even more longer than a recurrent neural network, where it just submerges information together, what if I have a even more better way of channeling data, or keeping the important data in hand such that the importance is considered or maintained over the entire sentence, even though the sentence is a little lengthy in nature. So that's what we have started to do. That's using a different mechanism known as LSTM. So basically, there are two varieties like LSTMs and GRU. So these are very similar network mechanism. As you see that it has many different gated structure that make shows the information goes into a perfect proportion. Okay, the proportionality of the data can be maintained in a much better way. Yeah, so let's try to understand this little better. So you have this in three inputs, right? So the one will be x, and the other one is going to be h of t. That's your previous state. H of t minus, that's your previous state output, and this is going to be c of t. Okay, this is x of t. So c of t, this is your like kind of a cell state. Okay, so where it holds all the raw information or all the information which has been read by this model, in this entire lifetime, not like entire lifetime, in this particular model training, how much it has learned, all these informations would be there in c of t. So the c of t will help LSTM to choose whether to retain the current state or update the current state with the new data, because the new data seems to be little more important than the previous information, or vice versa. If the input is not so important, what if I can able to retain the previous information like the same. So that's what this LSTM does basically. So you can see there are multiple combinations here, right? So one is like, you have, this is one combination, this is another combination, this is third. So basically we have three gates, like input gate, like, okay, forget gate, input gate, and output gate, I believe. Okay, or update gate, something like that. Okay, so you have three gates that maintains information flow. So imagine, like, you get a composition of x of t and h of t minus 1 together, that is concatenated together, and the information flows here, right? And if at all, if the sigmoid is becoming 0, because you can maintain the sigmoid, right? Sigmoid can give you value between 0 and 1. If I if I make sigmoid to be 0, the information of C of t will be lost. It will be becoming 0, which means that previous data is not important to me because the current data slightly seem to be important with that. Or usually, in a practical environment, the sigma will not be equal to 0. It will be like 0.1 or 0.2, like maintaining the proportionality of the data. Okay, so like how much proportion of the previous cell state to be introduced, and how much proportion of the input to be introduced. And very similarly, let's imagine, like, some proportionality of c of t enters here, and here also you can maintain how much proportion of the input to be added towards the c of t value. So here you can maintain it like keeping, like, let's say 0.1. Okay, if I keep it as 0, for example, if I keep it as 0, the whatever combination of these two information enters after tan h will be multiplied with 0 and loses up every information. That's basically 0, which means that, like, no information flows here. Okay, but again, since I have the sigmoid value is 0.1, certain proportion can be applied, or if it is 0.9 or 1, the entire proportionality of the data will go inside and adds up with the value c of t, right? So which is basically what's going to happen. So we can maintain the proportionality of the data by making sure or giving importance in terms of cell state, and also the input will be there. So you can add the input information within the cell state with the cell state by maintaining these proportions together. And finally, I can update these information whether to carry out this information to the next stage or not. The cell state remain unhinged. Okay, it will be unhinged after we add the new data together. So it holds, the cell state holds information of the previous data and the current data together. Okay, so that will be unhinged, but how much proportionality of this data should be flown to the next stage or the next time step, that can also be maintained. Because if I make this as 0, nothing will flow. Okay, so it will be like having empty values. So but practically, you'll have some values within it, right? So it will be like 0.1 or 0.9. So either the entire information will be flown, or just few proportionality few proportion of the data would be flowed. So that can also be maintained. So which means that the amount of data which is entering into the network can be maintained with this first set of gate, right? This gate. And the amount of data to be proportioned with the previous data can be maintained with this gate. And the amount of data that has to enter out of the network can be maintained with this gate. So with these three gated combinations, uh, you can basically have a better proportion to the data which is entering into the network, and the network can also gain good ability of retaining important informations over the period of time. So that way, LSTM proven to be more successful in nature because of the fact you can basically do uh, train with a large sequential data. And if at all you have a huge data set within you, LSTM is the way to go, because even now people are using LSTM to solve a lot of day-to-day problems. Even though we have this GPT models and other stuffs, due to the simplicity nature of this LSTM when compared to larger language models, LSTM proven to be more successful in deployment stage, where the memory constraint is a lot. So yes, LSTM, proven to be very successful as it can able to maintain information flow or maintaining the proportionality of the data at every period of time. Given the fact LSTM gained a lot of popularity, and it was introduced in almost all the important problems. And very similar to LSTM, we also have this gated recurrent unit, which is another representation of uh, another representation of gates basically. So which practically does the same of what LSTM did, but in a different way. That's all. Okay, so instead of having two gates, three gates, it potentially reduces it to two gates, where it can able to maintain the flow of information. The only difference is like the input and output only will be considered. There is no concept known as cell state. Cell state will not be there. You only have the input and output which is flowing inside. So based on this sigmoid and the tannage, especially based on sigmoid, you can maintain the information flow whether to keep it or not. Okay, so this is previous state data, this is the current data which is entering, that's x of t, and this is h of t minus 1. If I make this as 0, nothing will flow. If I make this as 0, the entire data will flow. If I make it as 1, 1 minus 1 will be 0, so that nothing will be flowing outside. So very similar fashion can be given in terms of gates in a much more efficient way, I would say. But yeah, having said, keeping LSTM and GRU hand in hand, nothing seems to be like a huge trade-off between the accuracy point, I would say, because both are most more accurate models, but only like interacting with these two networks with the same data set would give us a better position and understand like which network outperform which. But nevertheless, both are considered to be most popular and powerful network in handling sequential data. But it's not like the advancement of an LSTM network here. But I would say it is little simpler than LSTM, but not guaranteeing the fact it will be better than LSTMs. Okay, these are like hand in hand networks. But in terms of simplicity, in terms of complexity, I would say GRU gets a point, because you have lesser activation functions. You have only just two sigmoids and one tanh and few concats and pointwise multiplication. But when you see LSTMs, you had like three sigmoids and two tanh and multiple pointwise multiplication and additions, right? So which means that yes, GR is a little simpler nature. The memory footprint will be little less compared to LSTMs. But yeah, that's great. You know, I would say till some point of time. But still, I would say when you have a very lengthy sentence, imagine like you have 1,000 words in a sentence. LSTM can't handle that. It's definitely right because it's just proportions. It can't hold of information in terms of the proportionality, because at some point in point one percentage of flow will will add up more things when it reaches 1,000 time steps, which means that when you have too many words or lengthy sequence in a sentence, LSTM and GRU will fail miserably because it can't handle that much amount of sequence together. And the most important problem would be again the training time. It takes a huge amount of time to train. It's not basically it's not basically it has a very complex model, but it has a bottleneck at every stage. Because if you see this network, or any RNN based network, um, sorry. Yeah, I guess that was an interruption. Yeah, so maybe I'll just pause for a minute. If you have doubts in LSTM and GRU, just shoot it.
Hi Dipan, I'm Jaibalan here.
Yeah, hi
Um,
sir.
and which part amazing and that surely he will buy that that eatable package and all. And which part it is actually buying it again, that terms and all, where it is being captured in that LSTM networks. At which part it is identifying that it is going to take that word as an important or kind of that, how it is trying to identify that part.
Huh, that's a good question, sir. So, basically, like we have, let's say, like all these words are vectorized. We have it in terms of a number, and let's say, like the information flows word by word. Imagine the word amazing enters here, and you have a previous state at 0, basically. Now these two words will interact, like you have a pointwise multiplication, or basically you kind of add these information together, and that flows here. Now, initially the weight would be like, random in nature, right? So we won't have much ideology. But at some point of time, imagine these activation functions are, very tuned and can reason out important data. Imagine this amazing is a very important word. Considering the fact of the previous information, this holds more weightage, right? Which means that I would consider having, a value of zero point 0.9 here, zero point 0.9 here, and here can be very less. Why so it is very less? Because I feel like the current information is very important. I will try to limit the previous data. Let's say previous data would be only zero point 0.1 proportionality of information will be entering here. And here this word amazing or the vector word will flow here with 0.9 percentage. This percentage represent like how much information is flowing from this word. So from like let's say 90% of information is flowing from 90% of weightage is given to this word, and just 10% of weightage is given to the previous information. Now the new word or this area will hold most of the information from this word amazing. This word amazing will be here, will be staying here, or in a much positive way, and it goes to the next stage. And again in the next stage, let's say you get another word because that's not very useful. So on that time, this weightage will be zero point 0.9, because the previous state information is very important to me because it contains a very useful word amazing, but the current stage word is not important. So I'll reduce the proportionality like to 0.1. So mm, making sure this important word stays in the memory lane, so that the information flow can happen over the period of time. So that's how it maintains. So the word amazing, the word perfectly balanced breakfast, so these are basically vectors that will spike every time, when you get these kind of words, especially when solving this kind of classification problem, because when we back propagate, there'll be a loss calculation, right? So during the loss calculation, these words put up together, if I have these words in the sentence, this basically contributes to a positive sentence. So that's how the network will basically learn. Very similarly, how it can able to align this information, that is using this LSTM. So like LSTM is making sure the information is flowing very properly by aligning or keeping the most important words, or I would say in a even more simpler way, I could take the word this amazing box serial perfectly, but so I would discard this word this of me, all these words will be discarded. Only this important words like amazing serial box and those things will be there. And slowly at some point of time, this box of cereal will also be losing its importance because it's not that important to me. I'll keep this word amazing, till some point of time. And again, it's not the word that flows entirely. It's just vector, and the proportionality of vector will flow. Let's say this word is converted to a number known as 100. Instead of flowing the word number 100, I'll be having just 98, something like that. So that's how the information flow will happen, sir. Hope that is kind of.
Yeah. Thank you, Deepan. Thanks
Yeah.
a lot.
Okay, sir. Thank you. Yeah, but yeah, so basically these are some mathematical representations, I would say. But the ideology is like, how do we effectively represent data or maintain the information flow in a much more effective way so that the previous state information is maintained. That's why we have this proportionalities introduced in terms of gates. You can maintain that very well, rather just blindly multiplying or adding two states together. That would lead to lot of change in these numbers. So in this way you can maintain that in a much more proper way. So that's why LSTM and DRU proven to be more successful in nature. But yeah, so do we have any other questions? All right. Yeah, so since there are no questions, so let me go for the next part. So as I was saying, like, yes, people can't train larger models, especially with this networks. Why so? Because the biggest problem is sequentiality. Imagine I have like 1,000 time steps. In order to get the 1,000th time step information, I have to wait till 999 time step, because I need to get the previous state and the cell state information, right? The cell state will flow. The previous information should also be there as an input, right? Or if what is get, I love x of t and h of t minus 1. Without getting h of t minus 1, I cannot calculate the current stage, which means that if I have 1,000 time steps, the 1,000th time step cannot be run in parallel unless I get the 999th time steps h of t, or the gradient value. Only if I get this gradient value, that can be given to this h of or the final data, which means that this is too sequential in nature, and there is a huge bottleneck of having information flow, making it to be very very slow. No matter like how much computational capability you increase, that basically doesn't do anything here, because there is a weight of information, right? So that's the biggest problem. So there is no parallelization happening here. It's like more of a sequential thing which is happening in these methods. And also, when I have too many lengthy sentences, basically the information flow will be lost at some point of time. Even though I have this gated values and things that can maintain proportionalities, at some point of time the proportionalities will be lost. So these are two major threats, I would say, and we couldn't able to process or proceed beyond this, because of these two problems. And that's why we didn't had better chat assistants or chat bots or something like that in 2017. But that was kind of been shackled by this paper known as transformer, that changed the entire course of RNN or entire course of NLP, I would say, in terms of handling data, in terms of training the model, transformer proven to be the most successful invention in history of NLP that created many more architectures, which is what we are seeing it as GPT or BERT, or or your chat GPT models or visual language models, or every aspect of this models have been inspired or been taken from this transformer network. So this transformer created groundbreaking methods or changed many things inside the architecture, making it to be very very effective in handling the data and also perceiving information in a much more better way. Let's understand transformer in a much detailed fashion, because as I told, the GPT model got evolved especially because of this transformers, and we did saw the evolution, right? So the gaps in different areas, like how the representations of numbers were, how the sequentiality of the data was handled, and how the proportionalities of the data maintained to maintain the memory lane for a lengthier sequence, but how it was still a threat given a huge sequence, and how it was giving a huge threat when it comes to training the model because of the sequential nature of the data or the network. So all these things kind of removed or maintained by this architecture known as transformers. Let's try to understand what this represents. This is the entire architecture of transformers. Okay, so basically this was intended to have two sequence, two stage networks, that is input and output layer. One input section that contains some blocks of uh, neural networks or neurons and stuffs. Second, similarly, I have another block, so where the information flows happening from input to output together. Okay, but let's try to understand this detailedly, by going step by step. The first most important thing about transformer is you can parallelize the information flow. It's not like like RNN. If I want to get the information, or if I want to train or push this data dog into the network, I have to wait till this two get completed so that I get this h of t minus 1 that flows to this dog. But here in transformer, that's not even required. You can push all the data together in a much more parallel fashion. You get all this information at a singular time. You don't have to wait for the previous data, but you can also get every information for every other data which you've given. So that's the most like that is the most important thing in transformer, because now the training time can be reduced, right? The amount of time which is required to train can be exponentially reduced, because there is no wait time. You don't have to wait for the previous stage informations. You can just directly feed in or get the vectors or get the results parallelly for everyone. But how did they achieve it? Yeah, we know about embedding space, right? So how you create numbers that basically represents a meaningful vector for every word of close relations. But there is one more sidetrack towards it. I would say, this is basically been derived using a network. The network will give you a number basically at some point in time when you train a network with a huge amount of data, like billions and billions of word corpuses. At some point of time, the network will gain an ability to vectorize word in a much more better way, or giving closely relatable numbers to the closely related words, like how ImageNet networks, right, like the VGG and other things, gained ability in terms of extracting important information from images, right? Those convolution layers gain this ability to extract important information. Very similar to that, training a large network with a large amount of data created an ability to convert into vectors in a better way. So that's what embedding space is all about right now. So it's not like manual, vectorization process. It is done using a network that is like kind of an intermediate output, I would say. But basically, it gives you the vectors for every other word. But that's not, essential, or that doesn't solve the actual problem, because the biggest problem is the context of information. Okay, the information of the particular word can change, or the context of the particular word can change based on the sentence or how we use it. Correct? Let's say, let's take these two examples. Like AJ's dog is a cutie, and AJ looks like a dog. So in this case, if I give the word dog, it gives you a standard input embedding, like you get these numbers. But in this first sentence, you are referring to the word dog, or you are just referring to the dog itself, right? Because you're talking about that particular dog, it's being a cutie. But in the second sentence, you're not talking about the dog directly here, but instead you are talking, or you are taking the attributes of the dog altogether. Correct? Which means that the word dog which you see here in this sentence might not be the same of what you see here. So these are two entirely different meanings, but the word is the same, but the meanings are totally different. That is uh, contextual gap. That is basically the contextual gap, and that cannot be solved with just embeddings, because embeddings can give you just numbers that as a close relationship to the other words which you have. But how can I solve this particular problem? Because without this contextual information, I cannot 100% understand information, because I get the same number for this dog and dog in this two sentence, but these two sentences are entirely different, and the network struggles to understand this information gap. And that's where another ideology was introduced, that's called positional encoder, which is basically they have encoded they have encoded a method that can include the position of the words in a sentence. Imagine you have like the word dog in the sentence, that's in the second word in the sentence. And similarly, like you have a word dog which is in the fifth word in the sentence. Now the positions are different, but the word is the same. But still, I would say with this position, the context of the word is changing. Correct? With this position, the context of the word is kind of changing because of the fact yeah, the context would have changed because of the fact of using words before that or something like that. Which means that if I can able to include this positional information with the sentence or with the word together, I can give more context to the word, right? I can give more context to the word just by just by giving this word with a positional information. Okay, so that's what's happening here. Okay, so basically this is a PE formula. It can be you can use any mathematical formula that gives you a positional information or a distance information, something like that. Okay, so all you do is like you just give the position of it, and you will give this is basically dimensional reduction. Basically the model uh, size, or basically the number of words in the sentences will be utilized, so that the value which you get is kind of normalized in nature. Okay, so but yeah, you can use any formula as long as you get some meaningful number given to every position of the word, that is you know uh, more than necessary towards it. Okay, so basically this positional encoder helps the model to grow or gives the context information to every word which you see, making it to be more reliable in nature. Instead of having just the word embeddings, this positional based information gives more context towards the word. But I would say, imagine if I add another word here, the position changes to 6 from 5, correct? But does it mean that the context change it? No, right? So that, yeah, that's is another open challenge, I would say. Still there is some room for improvement in terms of getting the right context. But this method, somehow proven to be better than the normal methods, because it is somehow giving you more information for every word, at least in terms of position, that proven to be more effective for the networks. That's all. So you just have the embeddings of a dog, you add the position information towards it, you give this information alongside your vector, and with that vector you get another a vector that contains positional information of the same word with the actual information, right? So which means that you have a embedding of dog that has a contextual information altogether. Now if I go back, now the vector for this word dog will be different, and the vector for this word dog will be entirely different because of the positional change, but the content stays the same, but the position is going to be different. With this, people created better contextual info for every word. Now that the word has gained more context information, I can go a little bit into the network part. But yeah, one thing which I forgot to add here is, since I know the position of every word in a sentence, I just calculate, I can just see it, right? So this is first word, this is second word, something like that, making it very easy and not dependable in nature, because I can calculate the vectors for every word parallelly just by giving the positions, right? So I usually get the embeddings, and once I get the embeddings, I can give just feed in the positions of every word, and I get the embeddings for every other word, which means that it's not sequential in nature, it's parallelized. That's one thing. And here this is what happening. So you have an input embedding and you do a positional encoding, right? So positional encoding is done right now, so you get word informations or words that has a better contextual information. Now comes the most important part. Okay, so that's the attention mechanism, so which was introduced in another paper, I would say, from Meta. So they were trying to use attention mechanism with LSTMs, but it was not very successful. So that's why Google created this paper known as transformers, or attention is all you need, because they proved that you don't even require a standard architecture like RNN and LSTMs. You just require the attention mechanism. That's why the paper says that attention is all you need. Now let's try to understand like how attention works. Okay, so imagine this is the sentence I have the sentence, the big red dog. Okay, uh, what I do, I'm going to do a self attention mechanism. I'm going to take every word of the sentence and place it like this and keep the entire sentence towards it. So I'm going to look for the attention of this word to the sentence. Since it is a self attention method, the focus will be always staying on the same word all over again. Okay, so if you see the word the has more focus on the same word because both are the same. So yeah, that's a downfall of self attention. But the most important thing is like, what's the next important word? If you see, the next important word, or the most bigger number than the initial word, is this one, that's 0.18, that's basically dog, which means that the focus of the next word is going to dog for this word the. Similarly, the focus of this word big goes to the next important word on a stock, and for this third case also it is dog. But the final case, it loses importance because the word itself is dog. So you get a very huge percentage of value here, and you get equal representation for all these three things. So the attention mechanism is something that can focus which words are important in the coming stages and which words are not. So in this case, when I use the word the, big has less attention, the red has less attention, but dog has more, because I'm focusing on the word dog because the subject is all about dog. So I have to focus more about the dog. So once I focus more about the dog, I will focus about the attributes of the dog, if at all it is important. Based on the importance or based on the expectation which I have for the network, the attention vectors will focus its direction towards that way. Okay, in this way, the attention can be calculated for every word in the sentence. Again, if you see here, the attention can be calculated indigenously for every word without waiting for the later stage outputs, right? Which means that this can also be parallelized It doesn't require any sequentiality, right? So it doesn't have any penalty here. It can be maintained in a parallel fashion. And this is how the
Sir, one doubt in that vector, it should be total should be one. Is it the
yes, ma'am.
total? Always the total should be one.
Yeah, the total, it's like a probability representation. So the total will be one.
One. Okay, sir. Okay, sir. Okay. Sir.
Yeah. Yes. So any other doubts? Okay. Yeah. So now the attention vectors are created for the sentences. And this is how the attention mechanism works in the backend basically. So if I summarize it a little easily, we have three important aspects like V, K, and Q. Okay, Q stands for query, K stands for key, and V stands for value. Okay, it's like Q is something like it's like a query, right? So it's like a this represents the processed information of the current word. Okay, it's like it's a scoring process to see like how relevant other words are to the current word. Okay, so this query will make sure how relevant is the current word to the other words in the sentence. And key, this represents the information of all the words in the sentence, like it contains all the words information including the current word, and it is used to compute a score that represents the relationship between different parts of sentence. Okay, so it's not going, this is going to look for the relevancy, and this is going to look for the relationship between different parts of them. Let's say like the word dog, which words have more relationship towards it. Let's say the word big and red is important because these have some relationship between, right? So likewise that relationship can be captured with this word key. And value, it represents raw information, like it contains all the words in the sentence. So once the scores between different part of sentences are computed, they can be used to weight the value matrix. So if you see here, you get Q and K, you get all this multiplication, you scaled it, you mask it, you do all these things. Once you get this information, you push it towards the raw value. Okay, so the raw value will make sure the value matrix is represented in a much more aggregated fashion. Okay, because I cannot just look for just the like just for the importance and the relevancy of the word, but I have to maintain the value in a way so that I take the raw information V and keep it multiply it finally. So which means that Q and K will be multiplied. So basically these are some numbers and these are some numbers which will be multiplied. So the relevancy and the representative values will be going of the particular word, how relevant and how related it is. And based on that, you just multiply with the actual raw value so that you get something information. And one important thing here is like you divide this by a square root of dimensionality of the vector, because sometimes the dimensionality of the vector can be different for every word or for every sentence. Not to maintain the normalized value, you just divide it with the dimension. Okay, very similar to how we normalize the values, right? So that's what we do here. But nevertheless, so basically this gives you the actual value. So it's a very simple representation, but yet it is very powerful because it can get you attention vectors for every word which you get. And this is how the vectors looks like. For every word you get an attention vector, something like this. It's like how attentive the current word to this word and to the other words, and how relevant and how representative it is. So something like that. Okay, now that the attention vectors are calculated, you can pass this mechanism. So these are basically multi-head attention mechanism. So what is multi-head? So if you see here, instead of passing just one data, if you have multi-headed data, I can process more information parallelly and I can concatenate it together. That's called multi-head. So I can go with more heads, but more heads leads to more complexity because more parallel processing will happen. And because of that, the complexity or the memory requirement of the model training can be little tricky here. Okay, that's one thing. But having said, you can parallelize the process. You can calculate the attention vectors for all the words parallelly. if at all we have multi-head, 4 multi-heads or 3 multi-heads, you can do a lot of information in a parallel fashion, which means that this is also not sequential in nature. You can maintain the parallelism. Okay, and then you just do some normalization, because usually after self attention there will be like too much focus to given towards the same word. So in order to reduce those kind of spiky informations, we use normalization to somehow maintain the number flow, not too spiky but having a decent transformation. And once after that, we use a feed forward network that basically maintains the data or regulates the data of how it looks like, because input data can be different and the output data can be different. So I have to maintain the information flow from input to output, right? So in order to maintain the size and maintain the information flow, I use a feed forward network that basically enlarges or reduces the information as per the requirement of my output, because the ultimate aim is to combine or do a translation, like from the word big red dog I want to convert into Lee Gross chain dog, which is basically some language translation. So which means that the outcome and the input and the output should match at some point in time. That's why we use a feed forward network that will maintain it, because you can control the output neurons, right? No matter like how many input neuron comes, you can control the output neurons. That is more effective to handle it. That's why we have a feed forward layer. And again, we do another normalization, so that overfitting can be reduced. Now that the encoding layer is done, similar process will happen to the decoding layer. And again, this is also parallel in nature. It's not like till this process can happen, because you will have the same step in encoder and decoder. Okay, you see, like you do output embedding, and so it's just like input embedding, and then you do a positional encoding, and then you do a multi-head attention. Till this process will go parallelly, and then the output of this layer will come here, and it will process and give you an output. So now, what are the additional things which we have in this decoder mechanism? So we have, instead of just multi-headed attention, we have a concept known as masked multi-head attention. Okay, so what does it do? So basically, if I give the entire word with the input, what happens? Every word will be matched against every other word, and the result will be like fixed at the even at the first stage itself. That is not a good or a healthy way, because sometimes the word can also interchange. Imagine in this case also, right? This gross represent red and this chain represent big, so it is basically interchanged. So if I give one word, if I introduce word by word, the importance of word will have a better relationship between the input. So when it goes to the input output multi-head attention, right, encoder decoder multi-head attention, this will hold better value. So that's why this masked multi-head attention is happening. So you see, like all the information are masked in the initial pass. That's for the first word. Second word, I get the first word and the second together. Likewise, I give one by one together. In this way, with masking, the efficiency of attaching input and output, or having an encoder decoder attention to be even more better. That's what happens here. So the output of the encoder travels to the input, and the output of this masked multi-attention will go here. Both will work in harmony in understanding the relationship between the two sentences, the input and the output together. So once the relationships are identified, you do a feed forward, you get an output. So basically, you just try to get the outcome which you're looking for. That's why we have a feed forward layer and the linear layer that will maintain the outcome which is expected. So overall, I give a data input and an output. Data will be flowing into this input layer and output layer. Both will process information till the stage parallelly, and then the output of this layer will be fed as an input to decoder part, and you can get some possible inputs and corresponding outputs. So here we have solved two important things, I would say. uh, with transformer, we kind of created a concept known as positional encoding that created better context information for the given words. Right, even though the word appears in different position of the sentence, the context changes, and we kind of capture it, but not very effectively, I would say, at this point. But still, one of the good method to go with. And also we created a more parallelizable nature, so that it can, information is as parallel as possible. It doesn't have to wait in queue for other stages to be completed. And very importantly, once we started training this transformer model with a large corpuses of data, the model became very effective in understanding the language. Basically, once the language is understood, you can do anything which you can do, which you want, right? Imagine English, and if I want to ask you to create a summary for a technical symposium, yes, you can do. If I want to ask you to do a summary for a non-technical symposium, yes, you can do. It's a matter of understanding what it is, and you can just articulate it very easily, which means that understanding the nuances of the language is very important than understand the task. Because if the language is kind of learned, the task can be easily penetrable inside the architecture. So that's what happens here. So basically, both the sections, like the encoder and the decoder section, became well versed in understanding the language and the context of it. Encoder understand the context of the words, and the decoder understand like how to map every word in English to every French word. So with these two attributes, it became a deadly combination. But it didn't stop there. I would say this was a revolutionary paper that changed the entire course of NLP and sequential networks, because now everything is parallelizable. It can hold more information, and context is also there, making it to be much more effective in nature. But it didn't stop there. People realized, what if I split these two representations separately? Because I feel like this encoder section is still powerful to handle more information if I can block more and more sections of this together. So that's what we got it as BERT. Basically the transformer got separated into two sections. That is, like, encoder part is considered to be BERT, and the decoder part is considered to be GPT. Basically, that's where we got this word GPT, generative pre-trained transformers. So basically, this is a decoder representation, this is an encoder representation. So they just stacked more and more and more layers of the same blocks, just like how you stack more and more layers of neurons to make it more complex, and to draw more informational gain. That's what happening is. So the BERT and GPT got separated, and it is proven to be more successful in their own ways. Okay, I'll just quickly go to this sections since the time is of the essence. Yes, BERT represents bidirectional encoder representation from transformers. So yes, it can able to solve many things basically. The basic idea is, like, uh, they trained BERT with a very large corpuses of data, so that this BERT network understand like how a language looks like. And the idea is like, they used methods like MLM, mass language model, and next sentence prediction. With these two methods, they train this BERT network. How do they do? Like, let's say, imagine you have huge corpuses of data, right? You take a sentence, you mask two words in a sentence, and you give to the BERT, and the BERT should predict the word of this masked sentence. And very similarly, if you have two sentences, I should say whether these two sentences are related to each other. If it is related, I'll give yes or no. So these are the two tasks given to the BERT model. And with a huge amount of data we have in the internet, right? So we can take any data like Wikipedia resources, so, newspaper articles, all the publicly available data repos can be leveraged, because the advantage of those repos are, like, it is grammar free, it has good content, good quality content. I can just simply take those contents and do this masking, and do this next sentence prediction, and give it as feed it to the network, and the network will learn automatically and understand like how a language looks like. Once the context is gathered, once the pre-training part is done, you can fine tune it with your own inputs. Let's say you can have a question and answer network where you just attach a simple neural network. Okay, this will stay the same. You won't be fine tuning it more. Okay, this will kind of be frozen. Only this will be learned from scratch. It's like basically just like a transfer learning. Okay, so that's what happens here. But in a little different way, because this will give you some contextual output, and from that you get it to be fed into neurons, and that neuron will give you the expected answer which you're looking for. Now this guy will be like a black box guy, so that because it's already been trained, I just use it to gather informations, and from that information which is coming out of the BERT, I can use it for some other applications which I can see here. Okay, so I can use it for Q&A, I can use for many different outputs basically. So now BERT became very successful because with the quality data you can train better models. But again, still, yes, it proven to be very successful than the predecessors like your transformers and other architectures. But still, there is one fundamental problem which I would say, and very similarly, GPT model got into play. Like they have also many people, researchers, especially Google, contributed towards GPT models, and it is also proven to be more successful. Very similar to BERT models because both are transformer architectures, right? So it has attention mechanisms, and most of things are kind of stays the same. So with that, uh, they were able to maintain better models, but the only issue is like the data requirements, because every time you wanted to train a model, like let's say machine translation, question and answering, you need to require a huge amount of samples every time. Literally every time you do a text summarization for a technical content. Next time if you go for the non-technical summarization, it is not working properly because it is too much focused towards the actual. So there is no generality in the network because it is kind of task specific at this point. It's not very fluidic in nature. It still requires too much data, and overfitting is very easy because you just feed the data and attention mechanism, the deal, right? So this guy will easily overfit for sure. And it's not very fluidic in nature. Basically, sometimes you have a number and which you want to convert into some other currency value, something like that. So these kind of fluidic information is little difficult for the model to grab on. Okay, so these are few things in terms of fine tuning. So which means that every time you want to train a model, you have to aggressively create a data set, of 1 lakh entries, and push all these things aggressively to train, making sure it's not overfitted and you have enough data to be to be trained on to get a decent model out of it. But as the world goes very fast, we need to have a most general model that can fine tune on its own, not fine tuning too much, but at least if it has a zero shot learning, once we train it onto a huge large corpuses of data, that should be the case. So that's where GPT-2 and meta learning come into play. Once after GPT-2, zero shot learning was possible basically, because this has been trained onto a huge, much more bigger corpuses of data, making it to be even more powerful than other networks which was there, which means that you can directly ask questions and get answers, and you can also guide it towards the answers which you're expecting, like giving some few samples, like few short learnings can be given. And GPT-2 was successful because of this meta learning. With this two combination, you know uh, GPT um, became very popular because of the versatility, uh, you know um, of understanding new tasks very easily, because this particular meta learning paved this way, because it is a technique where the model can easily adapt towards a new task, on a very diverse set of tasks also it can able to do that. So that's the concept behind meta learning basically. But yeah, I'm not going very deeper into that, but basically yes, it's like model agnostic method where you don't have to fine tune the network very aggressively, but you can quickly fine tune it to its parameters with a new task with very few samples. Okay, that way it gained a good ability. And again, GPT-3 came into play, we had 175 billion parameters. It's like 175b, it's like the bigger network which you can get with this many parameters and many word corpuses entering into play, like large language models entering into play, making it to be even more deadlier, because now it has access over almost all the data which is available on the internet, all the technical papers, public forums, all the informations are there. With that, it gained even more better ability, which means that quickly adapting to a new task is even more easier for this GPT-3 with the meta learning process. It becoming even more easier for the model to adapt. And that's what we see right now. GPT-3 can able to adapt to anything, right? So you give a task, you make it as a question and answering robot, it will do that. If you want to make it as a chatbot, it can do that. So people started to leverage this or bear the fruits of benefits uh, from this GPT-3, and slowly it grew to 3.5, 4, and many versions which is up to come. So few key takeaways. Yes, ChatGPT came into play, which is very popular. It's especially because of this HIL, human in the loop reinforcement learning. Making it to be people giving feedback, and based on the feedback, it fine tunes automatically with good attempts. On the given instructions. So with quick rewards, in reinforcement learning, making it to learn even more, quick learning curve was there by the model, and it became even more better and more stabilized. As more and more question asked, ChatGPT became very stable enough to give better answers. That's why ChatGPT became very popular than the other LLMs. And now, yes, people created many different models, like Llama models, Phi, Mistral. There are many different LLMs which is created, but everything is a variety of GPT models. And the only idea is like how it perceives information and how it can uh, being trained onto a corpus of data. More the parameters, more the complexity. We also have 500B, even we have trillion weight model that is very powerful. But the only problem is like once the number of parameters increases, the complexity will be too high. Even to load the model, we require a huge amount of RAM to load, huge amount of GPU to load. So these are few shortcomings of GPT. But yes, Llama came into play. That is a lightweight model. We have a 7 billion parameter model, which is a very simple model that can be used. And recently, like RAG pipelines came into play. Using RAG, you can fine tune in even in a better way for the aspect which you're looking for, because even though the GPT model has been trained onto a large corpuses, some data can be little new towards it, or the task which you're trying to establish. So for that, we can do a little bit of fine tuning, and for fine tuning, we can use a concept known as RAG pipeline. With that, you can fine tune your GPT models in a better way. But yeah, not only that, we also got vision transformers, another variety of another variety of transformer that can look onto images, basically, rather going in terms of a numerical or NLP representation. It can also be adapted to images very similarly, onto images. But here, the concept is very simple. They basically created into patches, and for every patch they give positions, and with that they push it to a encoder block alone. That's your bird block alone, and you get an output that was very that was giving better results. So you have two embeddings, like position and patch embeddings, because these are patches, right? Because once the patches are piece things together, that gives a good information. So with those additional inputs, it proven to be better in terms of understanding the nuances of images as well. And that's why we got this visual language models, where we have this digital models, those advanced models that can relate images and the text together. Because basically every part of image will become an embedding. Okay, let's say human being, that will become an embedding. So it will relate that embeddings toward the word. So next time when you ask something to create in terms of a text, from text to image, it can easily do that because of the embedding vector mapping from the words to the image embeddings together. So with these two information perceived together, you get visual language model that can create videos, movies, all these crazy things which is happening in the market right now. But yeah, so this is the evolution of GPT models. So do we have any doubts or clarifications?
Even Raj sir, that was a very informative talk. Thank you
Thank
very
you.
much, sir.
Thank you.
Participant side, any questions from your side, please raise your queries. Faculty members, any questions from your side, please feel free to ask. Sir, I hope no questions from participants.